Have you ever wondered what light really is? A question so simple, yet its answer led to a dramatic shift in our understanding of the universe. For the longest time, light was thought to be a continuous wave, flowing uninterrupted through space. This was the classical wave theory of light, a concept that had held its ground since the late 19th century. However, something perplexing was observed. Certain metals, when struck with ultraviolet light, discharged sparks with an ease that was unexplainable by the prevailing theory. This observation, later known as the photoelectric effect, raised questions that the wave theory of light couldn't answer. The mystery deepened as further experiments revealed that the energy of these sparks increased with the frequency of the incident light, not its intensity. And thus, the stage was set for a dramatic shift in our understanding of light. It all started with a spark, quite literally, in the late 19th century. The stage was set for an intriguing scientific discovery that would forever change our understanding of light. Enter Heinrich Hertz. In 1887, Hertz observed a peculiar phenomenon that would open the doors to a new realm of physics. He noticed that when ultraviolet light was shown on certain metals, they discharged sparks with greater ease. This was the first hint that there was more to light than met the eye. But the story doesn't end there. Fast forward to 1902, where we find Philip Leonard deep in his investigations of this curious occurrence. Leonard was a man of keen observation, and his studies led him to a fascinating discovery. He found that the maximum kinetic energy of electrons emitted from a metal surface increased with the frequency of the incident light. This was a crucial observation, implying that there was a direct relationship between the energy of these liberated electrons and the frequency of light. However, this was a puzzling finding. According to the classical wave theory of light that was prevalent at the time, light's energy was determined by its intensity, not its frequency. This was a conundrum. How could the energy of the emitted electrons be linked to the frequency of light, not its intensity? Leonard's observations were indeed revolutionary, but they also raised more questions than answers. On one hand, they provided compelling evidence that there was a distinct relationship between light and the emission of electrons. On the other hand, they contradicted the established understanding of light as a continuous wave. This was a paradox that needed to be resolved. But the question remained, why did higher frequency light cause a more energetic release of electrons? The stage was set for a new theory, one that would reconcile these conflicting observations and revolutionize our understanding of light. Enter Albert Einstein, a name synonymous with genius. In the early 20th century, this remarkable physicist provided a revolutionary explanation for the photoelectric effect. Einstein proposed that light was not merely a wave, but also consisted of discrete packets of energy known as photons. Each photon, according to Einstein, carries energy proportional to its frequency. To understand this, imagine a photon as a tiny energy packet zipping through space. When this photon encounters matter, it can transfer its energy to an electron. If the photon's energy is high enough, it can free the electron from the material it was part of. This is precisely what happens in the photoelectric effect. But why did higher frequency light result in a more energetic release of electrons? This was a question that puzzled many scientists of the time. Einstein's theory provided a simple yet profound answer. Higher frequency light means the photons have more energy. So when they collide with electrons, they transfer more energy, causing the electrons to be ejected with greater kinetic energy. This revolutionary insight explained the observations that had stumped so many scientists. It was a groundbreaking shift from the classical wave theory of light, emphasizing the particle-like nature of light. It was for this explanation of the photoelectric effect that Albert Einstein was awarded the Nobel Prize in Physics in 1921. The brilliance of Einstein's theory is that it not only provided an explanation for the photoelectric effect, but also introduced key equations that are still used in physics today. One such equation is E equals hf, where E is the energy of a photon, h is Planck's constant, and f is the frequency of light. This equation is a testament to the power of Einstein's revolutionary insight. Einstein's theory not only explained the photoelectric effect, but also led to a crucial equation. It's a testament to the power of human curiosity and ingenuity, showing us that even the most baffling phenomena can be understood when viewed from the right perspective. E equals sign HF is more than just a string of symbols. This equation is a cornerstone of quantum physics, springing from Einstein's explanation of the photoelectric effect. Let's delve into it. The equation E equals h times F outlines that the energy E of a photon is directly proportional to its frequency. F, the constant of proportionality, h is known as Planck's constant. This equation signifies that light isn't a continuous wave, but is made up of packets of energy, or photons, each carrying an energy proportional to its frequency. But wait, we have another equation in the game. Kmax equals hf minus w. Here, Kmax is the maximum kinetic energy of the emitted electrons, and W represents the work function, the minimum energy needed to liberate an electron from the material. This equation beautifully explains why an increase in light frequency, and not its intensity, leads to a more energetic release of electrons. These equations, simple as they may seem, had a profound impact on our understanding of the nature of light, leading to the concept of wave-particle duality. Light, it turns out, has a dual nature. It can behave as both a wave and a particle, depending on the circumstances. On one hand, light exhibits wave-like properties, such as interference and diffraction, as seen in phenomena like rainbow formation or the spreading of light passing through a narrow slit. On the other hand, in situations like the photoelectric effect, light behaves more like a stream of particles, with each photon independently interacting with matter. These equations didn't just revolutionize our understanding of light, but they also laid the groundwork for the development of quantum mechanics, a theory that provides a framework for understanding the bizarre behavior of particles at the microscopic level, something classical physics could not explain. This equation and the concept it represented had far-reaching implications. From the tiny world of atoms to the vast expanses of the cosmos, these implications have shaped our understanding of the universe and continue to inspire wonder and curiosity. Science isn't just about theories, it's about how those theories apply to the world around us. The photoelectric effect, for instance, is at work in many of the technologies we use daily. Take solar cells, for example. These harness the photoelectric effect to convert sunlight into electricity. When photons from the sun strike a semiconductor material in a solar cell, they liberate electrons, creating an electric current. This phenomenon is what powers solar panels, and by extension, any device that uses solar energy. Similarly, electron microscopes, which provide us with high-resolution images of tiny structures, rely on photoemission. By shining ultraviolet light on a metal surface, a beam of electrons is produced. This electron beam is then used to illuminate the sample, producing detailed images that far exceed the capabilities of traditional light microscopes. Night vision devices too owe their functionality to the photoelectric effect. Photocathodes in these devices convert incoming photons into electrons. These electrons are then multiplied and projected onto a phosphorescent screen, creating a visible image even in near total darkness. But let's delve a bit deeper. There's a critical frequency known as the threshold frequency, below which no electrons are emitted, regardless of the intensity of the light. This is because photons with frequencies below the threshold don't have enough energy to overcome the work function, the minimum energy needed to release an electron from the material. Interestingly, contrary to classical wave theory, it's not the intensity or brightness of light that determines the kinetic energy of the emitted electrons, but the frequency of light. Changing the intensity of light only affects the number of emitted electrons, not their kinetic energy. This major discrepancy with classical predictions further underscores the particle-like nature of light, a fundamental aspect of quantum mechanics. The photoelectric effect, once a perplexing phenomenon, is now a fundamental concept with diverse applications. As we've seen, light is far more complex and fascinating than it first appears. The mysterious photoelectric effect, where light interacts with matter to emit electrons, has been a crucial key to unlock our understanding of light. Our journey started with the pioneering observations of Hertz and Leonard, which challenged the classical wave theory of light. Then we delved into Einstein's revolutionary insight, which proposed that light consists of discrete packets of energy known as photons. This groundbreaking explanation won him the Nobel Prize in Physics in 1921. We also explored the key equations born from this revelation and the wave-particle duality of light. Lastly, we've seen how the photoelectric effect is harnessed in everyday applications. from solar cells to night vision devices. So next time you turn on a light, remember the incredible journey of discovery that led us to understand its true nature.